Alright, we will continue our topic on tension members, and here we will discuss in details what if the bolt configuration is a staggered one rather than the inline bolt configuration. When I say staggered configuration, it will look something like this. So let's say we have this first row, then the second row is actually staggered, as compare that to the previous discussions that we had, that is just an inline configuration. Now this, because of this staggered configuration, we're actually increasing the capacity of the section. Okay, so how does it increase the capacity of the section? Recall that in the net area equation we have this gross area minus the simply just the summation of the diameter of the of course that's the diameter of the hole, which is 2 mm larger than the bolt hole, times the thickness. Now here, if we try to draw this in a three-dimensional view, that's gonna be something like this, right? If it's an inline configuration, it will be something like this. But if it's going to be a staggered connection, then let's say this is, okay, let's convert this to three-dimensional figure. So let's say just a plate or a bar. Then if it's a staggered one, then um, let's include another bolt hole here. So that's gonna be something like this. Oops. Okay, so if we compare this to an inline connection, okay, so for the inline, the sectional area would be something like this. But for the staggered connection, then it will look something like this. So meaning that the failure plane on along, I mean the failure plane and the fracture area will be this section. But for a staggered connection, it will be something like this. So because of this diagonal line, then that's gonna increase actually the area. So meaning increasing the area would result to a higher capacity. Okay, so in staggered connections, we have to take account into this of this diagonal of this capacity provided by this diagonal area. Okay, so before that, we'll have to introduce some notations on the regarding these staggered connections. Now, supposedly we have these bolt holes. Now, the distance between the bolt holes along the line of, let's say, parallel to the loading direction. So this is our loading direction, and this distance is actually parallel to this loading direction. This distance is what we call as the pitch distance, or this denoted as S. Okay, so that's the pitch distance, and the distance perpendicular to the distance perpendicular to this loading direction is our gauge distance, designated as G. Okay, so that's gauge distance. Let's say this is gauge distance 1, then this will be probably gauge distance 2, and so on and so forth. Okay, so these this diagonal area, okay, so this diagonal area can be computed using s squared over um, all over 4g times d. Okay, so this is what we call as the stagger factor. So s squared divided by 4g, referring to the gauge distance, times the d, the thickness, and that's going to be the increase in the net area. So therefore, what our equation will be, okay, so therefore our equation will be a sub n is equal to a, the gross area, okay, the net area is equal to the gross area minus the summation of the bolt holes, um, the area of the bolt hole. So that's okay. By the way, when I say area of the bolt hole, I'm referring to the cross-sectional profile, or the area that's provided by the bolt hole, and not this area, this circular area, not that one. So this is the area provided by the bolt holes. This is a plus s squared all over g all over 4g times d. Okay, so take note, this 4g times d is per diagonal. So meaning if there are let's say 3 diagonals, then you're going to have um, three stagger factor. Okay, so now how do we know if that's gonna be a failure path? Okay, so for example, we have this configuration, for example. Okay, so what's gonna be the net area, let's say the failure path? Then it will produce actually multiple failure paths, and we have to evaluate those failure paths, um, and then solve for the uh, let's say the minimum area or the smallest area, because smallest area would mean less capacity. Okay, so failure path 1, it is possible to have a failure somewhere like this, or something like this. Okay, so if we draw it here, we can have a failure path in this line. Okay, and another failure path could be probably this and this. So if we try it here, that's the reason why I'm drawing the same thing over here, just to separate the failure paths. Okay, so this one will be another failure path, and then what else? I guess that's enough. So let's assume for now that in these conditions we have a let's say an equal gauge and equal, let's say, pitch distance. Okay, so let's write here we have an equal of, for example, we have 50 mm. Okay, so how do we know if that's going to be a failure path? Now, this would be related to the term lead line of bolts. Okay, so meaning your it's like you have to take these bolts in a group, so they are together, and if there's going to be a fracture, then that fracture should be, I mean, this group of bolts should be on one side, and the other would be, or what's left here would be I mean, there should be no bolts that's left on the other side. Okay, so that's the reason why I'm taking failure paths over here. So we cannot take failure paths something like, example, something like this. Okay, so we can't take this one. Why? Because there's a single bolt that's left over here. Although you can probably methods to solve that ones, but you have to include the capacity provided by this, probably by the bolt here. So we'll just um, take a group of bolts together. Okay, so you can you can take that on this left side, or you can also take that on this right side. Now if we have same, there's a pitch distance, distances and gauge distances, then that would be, I think that would be the same for both sides. But if you have different distances here, then probably you have to take or evaluate this failure path over here, right? So that's gonna be our uh, this will be our equation for the net area when there's a staggered configuration. Right now, so let's do a sample problem here. This is our sample problem. It's a C-shaped section, and we're given by this configuration. It's a staggered configuration, and the pitch distances are, um, I think it's just the same, 50, 50 in all distances, and we have this gauge distance that's 35, 80, and 35. The C section is 150 by 19, and it says here we have an A36, and the bolts, they're 5 pieces, 16 mm diameter bolt. The problem says we have to determine the net area, or the smallest net area for the C-shaped section as shown. Okay, so once we're given this, if we have this C-shaped destination, then we can go to the table and obtain the values. Okay, so now let's solve here. Let's say obtaining the values from the tables. Okay, so since we're just dealing with the area, the net area, then what we need is the AG and the thickness of the web. Okay, so the gross area here, we can obtain it from the table, and that's, if you go to the table, you can find that it's 2,470 mm squared, and the thickness of the web, that's T sub W, it's going to be this. The thickness of the web is given as 11.1 mm. Okay, so now we have that. Then let's solve. I think let's solve for the bolt hole area. Okay, so we're solving now for one bolt hole, and that's gonna be a area of bolt is just simply the diameter of bolt plus the 2 mm times the thickness. Now this one is 16 mm plus 2 mm, that's 18 times the thickness, which is 11.1, and we get 16 plus 2 times 11.1, that's 199.8. Okay, so now let's evaluate first the failure path, possible failure path. So here we can have actually two failure paths. Okay, so one failure path is this one, meaning it's it's fracturing along this section, and the other failure path would be fracturing along this net section. Okay, so since we have this diagonal line, then that's gonna include the stagger factor. Okay, so let's say failure one. Let's say this is failure A, B, and then this one would be C, D, E. So failure calculating area net along A, B. Okay, so our net area is just simply the gross area minus the bolt hole area. Okay, so this is 2470 minus, since we only have one bolt hole here, so that's just 199.8. That's an mm squared. 24 minus 199.8, that's gonna be 2370.2 mm squared. Now for the next, calculating the net area AN along A, C, D, E. Okay, so we have, let's solve first for the staggered factor. What is this distance? This is 80, and this distance is given as 50. So meaning that the staggered factor is s squared over 4g times t is equal to, the s is 50 squared all over 4 times the cage distance, which is 80, times the thickness of 11.1. So that's going to be 86.72 mm squared. Okay, so this is our staggered factor, and our cross area AG is 2470, and our area of bolt, since we have two bolts here, then that's gonna be 2 times 199.8, which is equal to 399.6. So therefore the A net is equal to 2470 minus this bolt area plus the staggered factor, 86.72. 2470 minus 399.6 plus 86 point, that's gonna be 2157.12 mm squared. Right, so here in this problem we have a lesser net area, so simply because we're not actually comparing it to the same bolt holes. I mean, the number of bolt holes. Here we're only passing through one bolt hole, whereas here we're passing through two bolt holes. So that's going to be less, but if we have problems like we're passing through the same number of bolts, then probably we're gonna end up, or we're gonna obtain a higher value of this net area because of this increase in strength due to this diagonal area. Okay, so that's just the method for solving this net area when there is stagger configurations. And take note, this stagger factor is applied per diagonal line. So for example, if you have another example, for example, you have this, let's say a random configuration, something like this, staggered configurations to the non-uniform distances, then you have to apply the staggered factor here 4g times t, then you have to apply another staggered factor here, squared 4g times t. Okay, so supposedly we have different pitch distance here and gauge distance, then that's gonna be a different value here. Okay, so that's enough for this net area. Now let's further go to this topic. Now, for example, we have an angle or an equal leg angle, and we have this bolt hole on this leg and another bolt hole on this leg. Then how do we compute the gauge distance? Okay, so this is the cross section, for example, and there's a label G sub 1, the gauge distance from this tip, or let's say from this point to this hole, and we have another gauge distance from this to this top hole on the other leg. Now, if you try to something like you have to rotate this leg, then this will be the view. So we have G sub 1, then we have this G, let's say G sub 2 or whatever, but another gauge distance. So to calculate this distance from here to there, so let's say if we are trying to consider the diagonal line here, then we have to solve for this, or we have to use this equation, G plus G sub 1 minus T. Now what is this T? T, that's the thickness. So where can you obtain this T? From the table. Okay, so the same goes true if we're dealing with, let's say, a channel, a C shape. Now let's say we have this bolt configuration. We have, if we lay out it in a plan, something like a plan view or a fabrication plan, then this edge will be this line, this edge will be this line, and the bolt hole, the distance from this bolt hole to the center is the G, and we have this G sub 1, the gauge, another gauge up to here. Now the distance from here to there, so again, if there's going to be a something like this, then what's going to be the equation for the gauge, for your total gauge, will be G plus G1 minus the thickness of the web. So that's basically the same as the equal leg. But for the I shape section, that's going to be different, because let's say we have this, we have the flange and we have this web, we have bolts along the web and we have bolts along the flanges, I mean on both sides of the flange. So we have bolt hole here and another bolt hole, and our web is in between. Now if we look at the plan, this will be the okay, we cannot draw this gauge distance because that should be the distance from here to there. Okay, so our equation for the gauge distance here, that's going to be G over 2, that's this gauge distance on the flanges, divided by 2 plus G sub 1 minus the thickness of the web divided by D. So if in our homework we have this problem, this type of problem, then you have to use these notations. Actually, I think this isn't included in our lecture handouts, so you can just refer to this for our homework. Okay, another concept, the last concept for this topic would be the concept of shear lags. Okay, so shear lags are something like a phenomenon, okay, due to we can just roughly say it like non-uniform loading or stresses on the net section. Okay, so for example, we have this bolts here. Now let's say this bolted connection is connected to a gusset plate, and this one is our tension member. And if we try to apply the load, we're not actually experiencing a linear, or not linear, we're not actually experiencing a uniform stresses here. Okay, that's not the case. Okay, because there's a presence of bolt hole here. Now, if you have taken this topic in mechanics of materials regarding the stress concentrations, then that's probably the reason why there's a non-uniform stresses here. And plus, of course, the loading. We're just assuming that it's somewhere in the centroid, but probably it's not. Okay, so let's say we have these loading conditions. So meaning that if it fractures here, it's probably that the computed area that we have here is not actually the actual area that's being or the actual area that experiences the loadings. So because of that, there's there will be a parameter to take account into this of this shear lag phenomenon that will produce this effective area. Okay, so this is our equation. A E is equal to A N times the U. So this U is different from the U that we used in the what was that, black shear equation. This one is the effective area, and this one is the net area, and this U is our shear lag factor. Okay, so it's actually somehow reducing. So instead of let's say we have solved this net area, then at certain conditions we have to find the value of this shear lag factor and then multiply that. So instead of, let's say, having a 1000 millimeter squared of area, since if we are considering this shear lag factor, then probably we're having like if the shear lag factor is 0.8, then we're actually having an effective area of 800 mm squared. So that's the point, the main point of this shear lag phenomenon. Right, so this shear lag factor, where can you obtain this? You can obtain this from the table in NSCP, and in this class, if we're unless otherwise given, uh, we'll just have to assume a shear lag factor of is equal to 1.0. Okay, so I guess that's all for our topic in the tension members. In the next week, we'll move on to the topics on bolted connections. Right, so see you next week.